Good afternoon. I'm Norman Wildberger here at the University of New South Wales, and this is lecture 17 in this History of Mathematics course. In fact, this will be our last lecture of this course. Today we're going to talk about topology and just introduce some of the basic ideas of topology, which is nowadays a very vibrant discipline, goes in many more directions than I'm able to give it shape to today. So roughly what topology is the study of continuous shapes. And we're especially interested in properties which are unchanged by continuous deformation. So, for example, one object that plays a very big role is the sphere. And in topology, the sphere is sometimes called S2. A two-dimensional sphere. Now, that's a very pleasant geometrical object, but in topology, we don't mind bending it, distorting it a little bit. So, for example, we could make it into a more elliptical blob, or we could even do something more dramatic. We could maybe make it into a dumbbell shape like this, as long as the motions that we're going through, the transformation is a continuous one that doesn't involve any cutting or slicing or anything extreme like that. Right. So as far as topology is concerned, these three are all the same. They are called homeomorphic, which is the word for being equal in the topological sense. So another example of an important topological object is the donut or the torus. And that can also be transformed continuously to get something that's homeomorphic. And one example of that is a coffee cup. So there's a coffee cup. Rather think of a rather thick cup. Think of the surface of that coffee cup. Then you can think of distorting the donut continuously. There's kind of the hole in the donut that we're getting right there. These two objects are pretty well the same topologically. The subject also has a discrete aspect, because another thing that we can do, say, to a sphere is we can change a sphere into perhaps a cube. So a polyhedron, a two-dimensional surface made out of polyhedra, or polygons that are glued together along edges and form corners. And so topology has a kind of continuous aspect, and also has a sort of discrete combinatorial aspect that are interestingly connected. And the subject perhaps starts with the most important concept, or at least the most important invariant in the subject, which is the Euler characteristic of a polyhedron. Say P. So this was introduced by Euler in 1752. And the definition is that the Euler characteristic is V minus E plus F, where V equals the number of vertices and E equals the number of edges, and F equals the number of faces. So for example, for a cube, how many vertices are there? Well, there's 4 on the top and 4 on the bottom, so there's 8 vertices altogether. How many edges are there? There's 4 edges on the top, there's 4 edges on the bottom, then there's 4 edges along the sides, for a total of 12. And there are 6 faces, 1 on the top, 1 on the bottom, and 4 around the middle. So if we calculate the Euler characteristic for the cube, we get 8 minus 12 plus 6, which is 2. And then it turns out that if we did it for something else, like for a tetrahedron, for example, here's a tetrahedron. There, the number of vertices is 4. The number of edges is 3 plus 3, which is 6. The number of faces is also 4. We get, again, 2. And more generally, we have the following theorem, that if a polyhedra, the polyhedron P is homeomorphic to the sphere, then its Euler characteristic is 2. So this is not just for a cube or a tetrahedron, but also for an octahedron or an icosahedron or a dodecahedron, which you can check. In fact, it's true for any polyhedron that basically has the shape of a sphere. So this is an example of a topological invariant. It means that if you change the look of the thing but don't change its topology, the number stays the same. Well, what about something that was a polyhedron, but maybe not the shape of a sphere, but rather the shape of a torus? So our torus or a donut, we can also cook up polyhedral type of objects that sort of look like that. So here's an attempt at drawing such a thing. So I have a cube, and suppose I drill a square hole in the cube. Okay, that's supposed to be a cube with a square hole drilled through it. All right, so you can still divide this up into polygonal regions if you like. So you have a whole bunch of faces, a whole bunch of vertices, a whole bunch of edges. So you might like to check this out. So the theorem is that if the polyhedron P is homeomorphic to a torus, then its Euler characteristic is not 0 anymore. It's not 2 anymore. It's rather 0. In other words, if you were a bug living on some strange planet, and you had this idea, well, am I living on a sphere, or am I living on a torus or something else? One way of doing it would be to make a map on the surface, and then to count vertices, edges, and faces. Form this alternating sum, vertices minus edges plus faces, the Euler characteristic. And then if you got 2, or you got 0, it would allow you to distinguish between various possibilities. So this is certainly a lovely topological result, but its topological significance perhaps wasn't really appreciated till quite some time later. The work of Henri Poincaré, great French mathematician at the end of the 19th century, who in 1895 clarified the topological aspect of what was going on with the Euler characteristic. And he realized that the reason why this sort of works is actually relatively simple. It's that, he said, suppose you have a sphere. Okay? And suppose that on this sphere you have, on the surface of the sphere you have a decomposition in terms of lots of little faces, which are all, well, they don't have to be regular faces, they can be different sizes. But let's say any two of them meet along an edge or along a vertex. Okay, so we have lots of little faces like this covering the entire sphere. And suppose we're using this polygonal map to compute an Euler characteristic. So he said, well, what happens if we modify this? So at present we have a certain map with a certain number of faces, a certain number of vertices, a certain number of edges. He said, suppose we come along and do the following. Suppose we add a new vertex here. Just we take an edge and we decide to add a new vertex. So that instead of this thing here being something with 4 edges, it now has 5 edges. So adding a vertex, what does that do to the vertices, edges, and faces? Well, the vertices increase by 1 because you've added a new vertex. And the edges also increase by 1 because instead of having 1 edge along here, you now have 2 edges. And the faces haven't changed. Well, that means that the Euler characteristic hasn't changed because this number has gone up by 1 and this number has gone up by 1 and those things cancel. So chi is unchanged. So that's what adding a vertex does. What happens if we add an edge? Suppose that we decide to add an edge from this vertex to this vertex. In that case, the vertices don't increase, but the edges do increase by 1 because you've added an edge. And the faces increase because you've split one face into 2. All right, now what happens to the Euler characteristic? Well, the vertices have not changed. This has gone up by 1. This has gone up by 1. The total effect is to leave chi unchanged. And that simple argument shows that you can go ahead and subdivide this any old way you want. Well, you can add edges, you can add new vertices, you can subdivide it in a whole bunch of ways, and you're guaranteed that this Euler characteristic is staying the same. And what that proves, or almost proves, is that if you have 2 different maps of the sphere, so one person has one polygonal decomposition and the other person has a quite different one, then if we sort of agree to make a common subdivision by sort of overlapping them and putting in enough new things so that they actually overlap to form a common refinement, well, then at the point when they're the same, the Euler characteristics are then going to be obviously the same, so they must have been the same to begin with. So Poincaré argued this way, that means that this Euler characteristic doesn't depend on the map, but just depends on the surface. There's a little bit of details to work out, especially in this step here, but that was a basic little topological insight into why this number was important. And at some point during the history of this story, people realized that in fact, quite a lot before Euler, Descartes had an idea which was almost the same as the Euler characteristic. So Descartes, in a letter to Leibniz, in 1676 studied curvature of polyhedra. And in this letter, it's clear that he has almost his finger on the notion of an Euler characteristic, maybe not quite. So this is a very interesting development. So let me explain a little bit about that. But I'm going to do it in a slightly non-standard way. So I'm going to give you the rational angle version. Which just is a little bit simpler and avoids having to use pi's. So let me just quickly renormalize angles for you. If you have an angle like this, usually that's 90 degrees or pi over 2. Let's agree today that the angle is actually a quarter. Okay, because you're going a quarter of the way around. And so this angle, or this turn angle, will be a half, and all the way around will be 1. And if we go in the opposite direction, we get negative. So in this direction, we'll agree that it's negative. That's just a rescaling of angles, which is convenient in a lot of places, and it's very convenient for this discussion. All right, so the first thing that we have to remind ourselves is if you have a triangle and you have 3 turn angles, tau 1, tau 2, and tau 3, and I'll put them all in the positive direction, then what is the sum of the turn angles? 1? No. A half. Right? Because the sum is the same as a half turn, 180 degrees. So the sum of the turn angles in a triangle is a half. And if you have a whole bunch of lines coming in, then this turn angle and this turn angle and all the way to this turn angle, these will sum up to 1. Because we agree that 1 surround is 1. Okay, so here's what Descartes essentially said. Suppose that we have a cube. And let's suppose that we're looking at one particular vertex, that vertex x. There are 3 faces that come together at x. Those faces make 3 angles, or have 3 angles at x. One of them is 1/4, because 90 degrees is a quarter in our system. So we have 3 angles of a quarter sitting here. I should put the angles in the middle. So the sum of the angles at this vertex is 3/4. That's less than 1, and it's less than 1 because the cube is not flat there. If they summed up to 1, then that would be this kind of situation. So the difference between the sum and 1 is some kind of measure of how pointy that corner is. So we can define the curvature of our polygon, let's call it P, polyhedron of P, at the point X to be 1 minus the sum of the turn angles, Ti, the angle at X. We can make that definition. So the curvature of the cube at X is 1 minus 3/4, which is 1/4. In comparison, suppose that we have a regular tetrahedron. So in a regular tetrahedron, what would be the curvature at a vertex? What's the angle of one of those sides, of one of those faces? It's 1/6 because it's a third of a half. Right? So that'd be 1/6. So here the curvature is 1 minus 3 times 1/6. 1/6 plus 1/6 plus 1/6. There are 3 such faces coming together. So it's 1 minus 3/6, which is a half. Okay, so suggesting that the tetrahedron is more curved or more pointy than the cube. Right? And you probably feel it. If you had to fall on something, you'd rather fall on the edge of a cube rather than fall on the edge on the point of a tetrahedron. But the interesting thing is, what happens when we look at the total curvature? The total curvature of the polyhedron is the sum of all the curvatures at each of the vertices. So the total curvature of the cube, what's that? Well, we said the curvature at any one vertex is 1/4. There are 8 such corners, so it's 8 times 1/4, which is 2. What's the total curvature of the tetrahedron? Total curvature of the tetrahedron. Well, we saw that any one corner had curvature half, and there are 4 corners. So the total curvature is 4 times a half, which is also 2. And in fact, the total curvature is always the Euler characteristic. So even if you work this out for an icosahedron or a dodecahedron or even some completely irregular object, there will be places where there's more curvature, places where there's less curvature. The total curvature will always be 2 if the thing is homeomorphic or topologically equivalent to a sphere. So Descartes, in his study of curvature of polyhedron, was pretty close to understanding or having a concept of this Euler characteristic, which is very closely linked to this. So maybe just mention that theorem, that the total curvature of a polyhedron is equal to chi, the Euler characteristic. And by the way, when you look at, the case where we have the cube with the hole drilled out, you might like to play around with what the curvature at one of these vertices here is. You can get situations where the curvature is negative as well. Curvature doesn't always have to be positive. So you can test this out. Negative curvature can occur too. But the total will still be the Euler characteristic. So the total curvature of this square with the hole in it, if you go calculate the curvature at all of the corners and add them all up, it's going to be 0. Because that's the Euler characteristic. All right, so there's the sphere, there's the torus. There are also other interesting topological spaces, and one of them is the two-hole torus. It's a donut with two holes in it. Or, in fact, you could have a torus with three holes in it. Or, in fact, with G holes. G-hole torus. These are all examples of two-dimensional surfaces. And the genus is the word used to describe the number of holes. And it turns out that the Euler characteristic of the G-holed torus is 2 minus 2G. If there's 0 holes, we're talking about a sphere. 1 hole, we're talking about a real torus. 2 holes, that'll be Euler characteristic minus 2, then minus 6, minus 8, and so on. So are these surfaces used for anything? How do they come up? How did they come up historically? Well, they came up in a rather unexpected way, in a completely different direction from the theory of complex functions, complex analysis. And that was the work of a great German mathematician, Bernhard Riemann, who had a very short but brilliant career. He lived from 1826 to 1866. He was at some point a student of Gauss, and he made remarkable contributions in many areas of mathematics before his early death due to ill health. And one of the things that he studied is complex functions, which was a very interesting theory in the 19th century. It had a lot of development. So we're talking about functions from the complex numbers to the complex numbers. And to understand some aspects of this, Riemann introduced an interesting geometrical idea. He said, well, instead of thinking about the complex plane in the usual planar way with 1 and I and so on, why don't we think in terms of a sphere? So if we put a sphere at the origin, and let's say we make it a sphere of radius 1, it's supposed to be a sphere of radius 1, then we can do the following. We can choose the North Pole, say, up there, and there's a South Pole down here. And we're imagining the equator to be the plane, the complex plane. We can make a correspondence between the plane and the sphere. And what we do is we just look at the plane from the North Pole. So for every point Z in the plane, we draw a line from the North Pole to Z, from the top of the sphere down to this equatorial plane. And that line is going to meet the sphere in a second point. Let's call it 5Z. What this does is it maps the plane onto the sphere in such a way that points outside the unit circle are going to get mapped to the northern hemisphere, the top part of the sphere, and points inside, like if Z is here, well then the opposite point will be down in the lower hemisphere. So 0 ends up getting mapped here. The unit circle is the equator, and this new point N Well, it actually doesn't get mapped to anything. It's a new point which we're going to call infinity. So this sphere is a representation of the complex plane together with a new point, the North Pole, or infinity. So S2, which is called the Riemann sphere, is the complex plane together with one more point at infinity. This has some advantages. For one thing, the sphere is nice and compact. It doesn't go off forever. So it means that points which were very, very far away in the planar picture are now simply close to the North Pole. So we can see the whole plane right in front of us. And if we have a function like, say, f of z equals z squared, we can visualize that in terms of a mapping of the sphere to itself. Because in fact, it also sends infinity to infinity. Because if the point is very, very far away and you square it, it's still very, very far away. So this function has a kind of continuous extension to the Riemann sphere. But actually, Riemann was not so much interested in function like f of z equals z squared, but rather in the inverse function. The inverse function, it's a square root function. What does this mean? What is a square root function in the complex plane? Well, it's a little bit hard to say because this is actually a double-valued function. If you have an ordinary point in the complex plane, say here, then there are actually two square roots. You get a square root by bisecting the angle and taking the square root of the modulus. So there's one square root, but the opposite point is also a square root. So a point z in the complex plane has two square roots. So this is not a single valued function, it's what's called a double valued function. In real analysis, we also have this problem when we look at y equals square root of x, or the same as y squared equals x. The graph of y squared equals x is a parabola that looks like that. And to get y equals square root of x, we just say, all right, let's forget about this branch here and call this branch the square root function. It's a little bit arbitrary. We ignore that other branch that's naturally there. But it's a lot harder to do that in the complex plane because why should we choose this one instead of that one? And if z is over here, what should its square root be? There's one over here and there's one over here. So Riemann had the following interesting idea. He said, well, let's see what happens as we go around. So let's look at the unit circle just to make life simpler. And let's look at the relationship between a number and its square root. So here is z. I'm now going to stay on the unit circle. And here is its square root. Well, here's one square root. Let's agree that just temporarily, the square root of this z is that one there. If we're on the unit circle, the square root is also on the unit circle. So that's the square root there. Let's imagine what happens as we drag z around the circle. As the blue point goes around the circle, let's say it's over here, then the square root will have dragged, and now it'll be there. If we keep going, by the time the blue one is over here, the square root is here. And by the time we're over here again, the square root is now over here. So when the blue one has gone around once, when the blue z has gone around once, the square root has only gone around half. So to complete the story, we should go around again, says Riemann. Let's just keep going. So if the blue one keeps on going now, well, now this square root can just keep on going until once we go around one more time, it'll be back there. So Riemann said, we really need to go around this circle twice to get the square root function properly. Okay, so you need to get z around twice to see the square root function properly. Well, Riemann was able to make that more precise. And so he had the following rather nifty idea. So he said, let's look at the Riemann sphere picture. So there's 0, and there's infinity, and this is the Riemann sphere. This is the complex plane union infinity. And let's imagine two of these, one inside the other, like two layers of an onion. And let's imagine slicing one of them open so we can see the other one inside. The other one also is attached at 0 and infinity, and it also has, we're going to cut it as well, so we're going to cut it open as well. So there's another copy inside here, and I'm going to cut it as well. So you have to imagine these two layers of the onion. We're slicing both of them, opening the two things. And by analyzing what he did over there, he said what we really need to do is think about going around. And as we go around once, we want, when we get back to where we started, we don't want to stay on the sphere, we want to go onto the second sphere. And then when we come around again, then we'll come back to the first sphere. So he needs to sew the spheres. So he's going to sew the outside to the, let's say, so we're going to go around once here, and then once we got to this point here, we're going to jump onto the blue inside layer, and then we're going to go around, and when we get to the outside of that, we're going to come back to the original layer. So you need to sew these two spheres appropriately this way, and then we get some new kind of object on which the square root function properly lives. So on this curious new doubled complex plane, this is where the square root function lives according to Riemann properly. This is now called a Riemann surface. And on this surface, f of z equals square root of z is a single valued function. Okay, so he saw that topologically this is really the same as this. Suppose we just take these spheres and we cut them like this. We're cutting holes in each one of them. So why don't we just think of one of them like this and think of the other one like this. There's the holes that we've cut. And we have to glue these two together. Topologically, what we're getting is a dumbbell shape, where there's the gluing that we just did. But the dumbbell shape is the same as a sphere. So topologically, this gluing of two spheres together yields another sphere. So you might think, well, that's not that interesting, or it's interesting, but it doesn't give you something new. But Riemann realized that if you tackled a problem or a function that was a little bit more complicated than that in the simple square root function, then something rather more remarkable happens. So if you look at the function y squared equals z times z minus alpha times z minus beta. Or in other words, if you're thinking of the function f of z equals square root of z, z minus alpha, z minus beta. So kind of a cubic equation. Then the same kind of story gives you a different picture. And in that case, what you need to do is you need to take the sphere and you need to cut it in 2 slices. One from 0 to, say, alpha, another one from beta to infinity. And then you need to glue this to a second copy, also from 0 to alpha and from beta to infinity. So you need to glue these together along the same way that we glued these 2 together. But now there are 2 cuts. So the corresponding picture to this one is this one here. Let's see if I can draw. So there will be 2 cuts. So there's one sphere with 2 cuts, or 2 holes sort of made, stretched out. And then another sphere all oriented like this. Here are the 2 cuts. We join those. We join those. And lo and behold, what we get is a torus. So somehow, magically, this cubic curve in the complex plane gets associated with a torus. And this turns out to be a major insight into 19th century mathematics and has many, many consequences. The cubic curves are intimately connected with the geometrical object called a torus. Question?
Like before you look at the beginning, right? Like for 2 like shapes to be like polynomial, morphic, whatever, like you can't cut it and stuff, right? So like with these, like that involves cutting. So how do we consider those? Like how do we consider those polynomial?
Okay, so the question is, haven't we done some cutting, and didn't we say that cutting was not allowed? And you're quite right. We have at this point we've cut things. At this point we've cut things. But the point is that once we do our cutting and then we glue them back together, at the end we get something that's a torus.
Yeah.
The cuts have all disappeared, or they've been mended, if you like.
Yeah.
And now we're back in the nice realm of a nice surface. So at some point in the process we did some cutting, but then we overcame that problem. All right, so this is a more advanced material, and I've gone very quickly over it, so you don't need to get complete understanding of it. I just want to give you a sense that from the complex analysis point of view, there's some remarkable connection between cubics and a torus, and it led 19th century mathematicians to say, all right, what other surfaces appear in complex analysis, and more generally, what are all the surfaces? Can we list all the surfaces that might possibly arise in investigations like this? So there was the problem of the classification of 2-dimensional surfaces. And we're talking now about surfaces that are compact, so they don't go on forever like a plane, but they're all sort of contained in a box. And there's a short list, well, there's a list of them. It's not short because it keeps going. The first one is the sphere, and then there's a torus, and then there's the 2-hole torus, and then there's a 3-hole torus, and so on. This is a complete list of all the compact, orientable surfaces. And their Euler characteristics: the sphere was 2, the torus is 0, this one is -2, this one is -4, and so on. However, I said orientable. What does that mean? Orientable means that if you're an ant, and you're living on one of these surfaces, you can distinguish between right-handed and left-handed ants. Okay, so here's a little ant, whatever there. So maybe this is a right-handed ant, and this is a left-handed ant. Okay, and as they walk around, even if this ant walked around, this ant would recognize, oh, he's got a big right hand. Well, this one has a big left hand. Okay? There's a notion of right-handedness and left-handedness on the surface of the on the surface. But there are surfaces that don't have this orientability property. And the first one of those was discovered by German mathematician Mobius. And here is my attempt at drawing a Mobius band. Okay, so it's what you get when you take a long strip of paper, and when you glue it together, you put a twist into it before you glue it together. This is a non-orientable surface. It's a rather curious thing. If you had an ant that was like this, the big right hand, and then the ant just walked around, by the time it came back, it would look like this. It would be a left-handed ant. Which means that there's no sense of left hand and right hand doesn't work on this surface. This is a non-orientable surface. Okay, but it's a little bit of a strange surface because it has a boundary. These surfaces didn't have any boundary. This is not exactly a nice proper surface because it has an edge. Let's look at the edge. The edge, if I start here and I go around, here's the edge. And then I'm going on the bottom, come around here, I'm still going around, and then come down here and come over here. I get back to where I started. The edge is one big loop. The edge is a circle. Not like for a cylinder, which has two circles as its edges. This one has one continuous circle as its edge. And that means that if you took a disk, which also has a circle as a boundary, and you glue them together, you would get something without any boundary. Now you can try this at home, but it might be a little bit dangerous because you would get all messed up. So you can make yourself a Mobius band, and you can cut out a disc, maybe made out of some cloth, and you can start sewing. So you can label this, right? Maybe you can label it to 0, and then maybe a quarter, and then a half, and then 3/4, and then back to 1. And you can label this from 0, a quarter, a half, 3/4, and then back to 1. And then you can just glue or sew the 0 to the 0, the 1/8 to the 1/8, and so on. Do some sewing. But you will find that you get messed up. As you get closer to the end, the thing is twisting in some way that the object gets in its own way, preventing you to complete the sewing. So you can't actually complete the sewing in 3-dimensional space, but you can in 4-dimensional space. So if you lived in 4-dimensional space, you could glue these things nicely together, and then you get what's called a projective plane. What's it look like? Well, we can't draw it. I can't show you a model of the projective plane because it doesn't exist in 3-dimensional space. Okay? But there is this thing, and so I'm going to draw it like this. Okay, it's like the top half of a sphere. And another way of thinking about it is you take the equator and you identify opposite points. So it's, or maybe another way of thinking about it is to think of it as a sphere together with this sort of strange sort of figure 8 thing called a cross cap. So that's the projective plane, which is a rather strange thing, but very interesting. And then there's other non-orientable surfaces. The other non-orientable surfaces are what you get when you take these things and you add cross caps to them. So you take a torus and you add a cross cap. And then you take a 2-hole torus and you add a cross cap and you keep going. So this is then the list of all non-orientable surfaces. And this was all finished in around 1907 by Dean and Heegard. So that's the classification of all two-dimensional surfaces, a list of compact orientable ones, a list of compact non-orientable ones. The Euler characteristics here, you can still talk about Euler characteristics. Chi equals 1, chi equals 0, chi equals -1, chi equals -2. They go down by 1. So it's a very attractive, interesting classification result that has motivated a lot of 20th century work in algebraic topology. In particular, people have worked very hard to try to understand what might be going on like this, not for two-dimensional surfaces, but for three-dimensional surfaces, where it turns out things are much, much harder. And we are very far away from having a classification like this, even today. We do not have a classification of three-dimensional surfaces. Yet there's an interesting point maybe that I'll finish mentioning because it was in the news 10 years or so ago. And it has to do with a property that the sphere has that none of the others have. The sphere is distinguished amongst all the two-dimensional surfaces in having a certain property. And that property is that it's simply connected. What does that mean? It means that if you draw any curve, any closed curve on the sphere, actually on the surface, you think of it as like a string, then you can shrink that string continuously on the surface to a point. Staying on the surface, you can just shrink it to a point. That's not true of a torus, because it's true for this kind of curve. That curve you can shrink, but this curve you can't shrink. The hole in the surface prevents you from shrinking that thing to a point. So this is the only surface that is simply connected. And probably a good place to end is with the famous conjecture, the Poincaré conjecture, which is that the three-sphere is the only simply connected three-dimensional surface. Okay, simply connected in the same sense, meaning that if you have a loop in a three-dimensional sphere, you can contract it to a point. This was a very famous conjecture, 20th century mathematics, and it was solved in rather spectacular fashion by a Russian mathematician, Perelman, who in 2003, I think, something like that, he posted 3 online papers that gave a very complicated and interesting attack on this, working on or building on the work earlier of mathematician Hamilton. And Perelman got a $1 million prize for this. He's living in Russia, I think in St. Petersburg. But rather spectacularly, he refused the prize for various reasons. So there was a lot of controversy and interest in this conjecture, which was proven. So this is a whole aspect of a subject called algebraic topology. And if you're interested more about that, I do have a YouTube series of a course I gave last year, which is an introduction to that subject. Okay, so that's a very brief introduction to some of the ideas in topology, going back to Descartes and Euler, and still very important in modern physics and other things. And so with that, we end this a course in the history of mathematics. Of course, there are many other interesting topics in the history of mathematics, but I'll have to leave that. Some of them are more advanced. So thanks for your attention.